Welcome back. In this lecture, I will complete the characterization of polymers module, and I will discuss about mass spectroscopy of polymers and chemical characterization. So, in this lecture, I will talk about mass spectroscopy of polymers, specifically MALDI of MS, and chemical characterization will be restricted to NMR methods. In general, mass spectroscopy involves study of mass of ions created by ionization or fragmentation and determined electrically at the gas phase. And this spectrum in this mass spectroscopy is a plot of ion abundance against mass to charge ratio, or in simple we call M by Z. Conventional mass spectrometer for low molecular weight compounds, the energy of the electron beam used is about 8 to 13 electron volts. Now, in case of polymer, if we use this large electron beam to fragment, polymer might degrade before vaporization. Now, that will complicate the situation further. In case of small organic molecules, we know that all the molecules have same molecular weight. So, if we fragment, the larger fragment will be of course coming from the molecular weight itself, the entire whole molecule itself. But in case of polymer, the sample consists of anyway many molecular weight polymer chains. So, if you fragment a particular polymer, then we do not know whether that fragment is because of fragmentation of a polymer chain or it is present originally in the polymer mixture. So, use of mass spectroscopy in polymer need to be such a way that the polymer samples should not be get fragmented during the measurement. We should be able to measure the molecular ion or the entire polymer mass of the entire polymer chain, so that we can get the size of the entire mixture of polymer molecules. For that, modified mass spectrophotometer are used for synthetic polymers. In this case, soft ionization is done, and that is done using a matrix. So, we call matrix assisted laser desorption ionization. I will discuss in little detail this process, and the time between detector and the origin is actually measured. That is why we call time of flight TOF, and the price of this mass spectrometer is much higher compared to the conventional mass spectrometer, which are used for determining the molecular weight of small organic molecules. So, in short, we call this as MALDI of MS. Now, as I discussed that in this case we cannot fragment the polymer chain. So, if soft ionization is required, for that a dilute solution of polymer sample is mixed with a more concentrated matrix solution, and the typical matrices are aromatic organic acids, and small alicot of this mixture is applied to the MALDI plate, and it solidifies as the solvent evaporates. Once solvent is evaporated, we have the mixture of polymer sample and the matrix. Now, the plate is placed in the source of mass spectrometer, and short pulse of high energy laser irradiates the target. That means, this mixture by irradiating it actually vaporizes the matrix. Now, once the matrix vaporizes, it carries the polymer which was immersed in this matrix. So, it takes the polymer in vapor phase, and in the vapor phase the matrix gets dissolved from the polymer molecules. So, we have the polymer molecules in vapor phase, and polymers molecule need to be charged so that it can move under electric field. So, neutral polymers are ionized by protons or small cations like sodium, potassium or silver ion. So, once we generate these charged molecular ions, then we apply a detector, and the time it takes to move from the source to the detector is what determine, and we call this is the time of flight. And obviously, the time will be taken more by the larger molecular weight than the smaller molecular ions. So, ions are formed in pulses, and all molecular ions follow exactly the same path to the detector, and the detector measures the time for the ions to reach the detector. That is why the term time of flight is used for this technique. So, this is a typical multi-top spectra for low molecular weight PMMA. This technique is mostly useful for low molecular weight samples, because if the molecules are very large or high molecular weight sample, then using a proper matrix to carry them to the vapor phase is difficult. Hence, it is mostly useful for low molecular weight sample, but it does not mean that it cannot be used for high molecular weight. Using proper matrix and trial and error method, it is possible to use this technique for high molecular weight as well. This is example of multi-top spectra for low molecular PMMA, and in this case you can see that difference between two molecular ion is 100, which is the molecular weight of the repeat unit of PMMA. This confirms that this spectra is from PMMA, and from this distribution we can get the values from Mn, Mw and so on. So, the matrix material is very critical in this technique and needs to be optimized for each polymer. That is the disadvantage, that there is not general rule, that there are some guideline or some kind of guideline from prior experience, but there is no hard and fast rule that the particular matrix should be used for a particular polymer and so on. And uniform solid solution with the polymer and the sol has to be there. The matrix has to strongly absorb the laser in that particular wavelength, and it also give rapid vaporization. The sol for cationation also need to be selected based on polymer structure. Generally, polyester, polyamides, polyacrylates, sodium ion, potassium ion used. More hydrophobic polystyrene, polybutadiene, silver ions are used. Polyethylene, polypropylene, they are very difficult to ionize using this technique. So, this technique is not very useful for determining the molecular weight of polyethylene, polypropylene. And some cases the solubility of the polymers are not good in solvent, which need to be used for making a mixture with the matrix. So, that is difficult. So, this technique is not useful for those polymers. And solvent must evaporate quickly to give a uniform mixture. And these are typical example of the matrix which are used for this technique. Next, I will move to the chemical analysis of polymer using NMR. There are other spectroscopic technique like UV visible and infrared spectroscopy which can be used to do chemical analysis, but the use of NMR is much more practical and much more useful because use of IR and UV visible spectra is very limited. These are limited to determine the functional groups or chromophores present in the polymer molecule itself. Now, those of you do not know NMR spectroscopy, this is just a quick basic guideline that NMR is about the transitions between magnetic energy levels of a molecule, and the thumb rule is that which type of molecules are NMR active, that only nuclei with spin number which is labeled as I not equals to 0, they can absorb or emit electromagnetic radiation, and atoms which have even atomic mass and number, they are not NMR active because their I is 0, like carbon 12 and oxygen 16, those are the most abundant atoms in carbon and oxygen. Whereas odd atomic mass gives you I is equal to half integers, they are very common, they are useful for NMR spectroscopy like proton, carbon 13, nitrogen 15, phosphorus 31, or even atomic mass and odd number that gives you whole integer like nitrogen 14. This can be also used for your NMR spectroscopy. And these are the parameter which we obtain from a NMR spectrum, and this is just again this is a simple guideline for those who are not very habituated with NMR spectrum. The number of signals or peak in a spectrum is related to number of equivalent group of atoms. For example, number of equivalent protons or carbon 13 present in that molecule. The frequency or the ppm of the signal, that means the place where it is appearing, the position of the signal is related to the chemical environment around that atom. The intensity of the signal is related to the number of atoms that are contributing to the signal. The line splitting of the signal gives information about the neighbor, and line shape, the peak line shape gives information about the interaction with solvent, and there are some specific semi specialized techniques are used which are not very common, but they are used for special purpose. Relaxation time T1, T2, information about polymer dynamics, and NOE which gives you the information about the spatial arrangement of atoms, which helps us to find out the conformation, polymer conformation and so on. We can use NMR spectroscopy NMR spectroscopy is actually used in great detail to identify the polymer and the functional groups which can be used to monitor the progress of polymerization process. It can be used to find out the tacticity, whether it is syntactic, isotactic or atactic polymer. It can be used for determining copolymer composition, chain molecular structure in copolymer, whether it is a random copolymer, alternating copolymer, block copolymer. And it can be also used to find out the N groups, and also it can be, if there are N groups are basically as we mentioned in earlier class, earlier lecture, that if the N groups are having some attributes, then we can use this N group analysis by NMR to determine the molecular weight Mn, number average molecular weight as well. This is example of PMMA NMR spectra, and if you see this structure, this is a proton NMR spectrum. So, we will only concentrate on the protons. There are 3 types of protons present in this molecule, one here, 2 protons, and this is 3 protons, and again 3 protons. So, they will have 3 different peaks. So, this peak is here, this is here, all 3, and this is here. Now, this methyl can have different stereo arrangement in relative to the next repeat unit. Remember, we talked about different possibilities: syn diatactic, where the arrangement, stereo arrangement is same, alternate; isotactic, when the stereo arrangements are same, and atactic, where there is no particular order of stereo arrangement. Now, in a particular sample, it may not be the case that we have exclusive arrangement of syn diatacticity or atacticity or isotacticity. By comparing this intensity of this signal, which corresponds to one particular arrangement, like RR corresponds to syn diatactic, corresponds to isotacticity, this corresponds to atacticity. In that case, we can actually find out what is the extent of tacticity. For example, in this particular sample, the contribution of RR is much higher, which means that this particular sample is predominantly syn diatactic in nature. Now, I have discussed this earlier, how to use N group analysis using NMR to determine molecular weight. So, I will not go through this in detail, just recall that in this particular polymer, as I explained earlier, the molecular weight was found to be 8500, and number of this N isopropyl acrylamide unit or the value of N was found to be around 75, and this was done by comparing the signal of this particular proton here, A proton, which is exclusive to this monomer, to the protons present in this N group. By comparing these intensities of these 2 protons, type of protons, we can get the value of N and hence the molecular weight, which I discussed earlier. Now, we can use a similar technique to find out the copolymer composition. Now, in this case, we have added a second block, dimethyl amino ethyl methacrylate. So, this is the second monomer which we added after the first block was synthesized to make a block copolymer. So, in this is a block copolymer of dimethyl aminoethyl methacrylate, in short DMEMA, and poly N isopropyl acrylamide, as we discussed here. Now, this D proton, which has signal here, this signal at around 4.06, it has contribution from this proton as well as these protons, 2 protons from this unit and 1 proton from this unit. whereas this peak at 2.3 corresponds to these 6 methyl protons, and this peak at 2.6 corresponds to these 2 B protons. Now, you can also see that the 6.6 protons give you a intensity around 3, whereas 2 protons give you a intensity around 1, which basically kind of satisfy the internal calibration, though it is not perfect, but it is nearly same. So, in this combine this signal, which is contribution from both this monomer, this proton D proton as well as A proton, we can use this signal to find out the composition of this polymer. So, in this case the intensity value is 1.35. Now, per proton we have seen we should get 0.5 as a signal. So, for the 2 protons here we should get a signal corresponds to 1. So, rest 0.35 must be coming from this proton. So, 0.35 contribution from this proton and 1 coming from this proton. Hence, the ratio by mole by number between these 2 repeat unit or the ratio of M and M must be 0.5 is to 0.35, or the degree of polymerization of this particular unit would be 0.5 into 75 divided by 0.35, because 75 is the value of N which we have determined in last slide. Hence, the number of units of this particular unit is about 100.07, or the value of M is 100.07. So, this is the example how NMR can be used to determine the composition. Now, this is for block copolymer, we can use the same technique to find out the composition in case of random copolymer or other types of copolymer, provided we need to have exclusive peaks for different monomers. We can use carbon 13 NMR to find out the type of copolymer. For example, this is a carbon 13 NMR for polycarbonate, bisphenol A polycarbonate, and each of these carbon are marked here. The carbon peak, which is interesting to find out the type of copolymer, is A, which is shown here, which will be utilized to find out what is the nature of copolymer. So, in this case we have a copolymer of bisphenol A and this monomer. Now, there is a 3 possibility in this case. If these 2 monomeric unit bisphenol and they sit next to each other, or they contribute to form this carbonate linkage, then this carbon will have different value than a combination of bisphenol A and bisphenol A, or this particular monomer with this particular monomer. So, from the value of intensity of this carbon signal, we can get what is the arrangement, what is the extent of arrangement of this kind or this kind or this kind in a copolymer. Now, in a statistical sense, if there is no bias between any of these arrangement, then because there is 2 way it can be formed, this should have weightage of 0.5, this will be 0.25 and this will have 0.25. In case the copolymerization is formed from a 1:1 mixture of these 2 monomer and there is no bias. But in this particular case we have used say 1:1 two monomers which are used in 1:1 by mole, and here this is one sample. In this case this sample this carbon has 2, this is 1 and this is 1, which means the ratio of intensity in these two cases is 1:2:1, which means in this particular sample this is a perfect random copolymer of these two polymers, these two monomers. Whereas in this case you can see that the signal of this particular carbon is lower compared to either of this or this. Hence, in this particular sample we can conclude that the chances or probability of block formation, that means one particular monomer is sitting next to same monomer, is much high. We can actually compare quantitatively by finding out the ratio of these signal intensities. So, this is not a random copolymer. So, by using this NMR technique we can find out whether the two monomer actually produces a random copolymer or a non-random blocky type copolymer. So, with this what we have kind of completed the characterization model, and if you remember the two types of characterization we have done. One is molecular structure, where we determine the chain dimension and molecular weight of the polymers, and we have found out the identity of the polymer mainly using NMR techniques. I have not gone through the other techniques which can be used to find out the microstructure more. There is a possibility that we can use the other techniques to find out the microstructure. With this I will conclude this lecture, and in next lecture I will start a different module on polymer properties.